Hello everyone, welcome back to Spectrum classes. This is my next video on the topic molecular term symbols. In my previous video, I have discussed about the molecular term symbol, and in that molecular term symbol we have discussed in detail about the parity or inversion symmetry about the center of symmetry of a given molecular term symbol, whether it is G-rayed or un-G-rayed. And we can also say this is G-rayed is symmetric about the center of symmetry and un-G-rayed is asymmetric about the center of inversion. And moreover, this G and U designations, which are written as subscript on the right hand side of the molecular term symbol, along with the total angular momentum quantum number, and this is applicable for the homonuclear diatomic molecules, number one, or to the molecules which are having center of symmetry. For example, CO2 molecule or C2H2 molecules, etc. So about this inversion symmetry, we have already discussed in my previous video in detail, and here in continuation to the videos on molecular term symbols, in this video we are going to focus on the reflection symmetry, right? So reflection symmetry is given in the terms of plus or minus as a superscript on the right hand side of the molecular term symbol, and it is applicable only for the sigma term symbol. And this sigma term symbol is formed by two different methods. So we are going to discuss one by one. This is not, this plus and minus reflection symmetry is not applicable to other term symbols. Now we are going to discuss this kind of inversion symmetry in detail. First of all, before starting with this reflection symmetry, I'll just bring to your notice that how this sigma term formed. So this sigma term is formed when we are having the orbital angular momentum quantum number is equal to 0, and this orbital angular momentum along the internuclear axis. So when we are having this lambda is equal to 0, then we are having this sigma term. Fine, you all are aware about this term. Now the question comes how this lambda is equal to 0. So this lambda can be 0 if our electron is entering in the sigma orbital. So for sigma orbital, we are having small lambda is equal to 0. This is one way. If it is in sigma star, then again we are having lambda is equal to 0. The other way, if we are having electrons in the degenerated pi orbitals. So if this is pi plus 1 and this is pi minus 1, and 1 electron or paired electrons are in these two degenerated orbitals, then we are having this lambda is equal to 0 again. So these are the methods through which we are having this sigma term. Now coming to the next. So I will give you how this sigma orbital is symmetric about the center of symmetry. So as we discussed earlier, this is the polycentric molecular orbital, and it is having the same color about this internuclear axis, or it is having plus plus symmetry. So if we are having the reflection in this plane which contains the internuclear axis, then above the plane we are having plus sign, and below the plane on reflection we are having the same sign. That is why this is symmetric about the reflection. Therefore, if the electron is present in the sigma orbital, then that will be termed as sigma plus. If it is in the sigma star, so sigma star is formed like this, and this is the reflection plane or internuclear axis, and if the plane through which it is reflected, so suppose it has symmetry plus 1 and this has symmetry minus, then only we are having on reflection here it is minus and here it is plus again. I will show you in the next example. This has same symmetry, or it is symmetric about the reflection, therefore this term is also termed as sigma plus. Now I will take the example of pi. So these two are the pi orbitals. You can understand this is say plus and this is minus. This is plus, this is minus. On combination they will form, this is the internuclear axis, they will form this kind of sigma orbital. This is designated as sigma orbital, right? So this sigma orbital, if we are passing through, or if we are going to see this reflection, so above this we are having this green sign, and below this plane, which is xz plane here, which is having the internuclear axis, so we are having the same. So you can imagine this analogy. This is the three dimension, a cylindrical type of picture is there, and we cut down it about this internuclear axis, we will have the same kind of images. So if we are getting the same kind of images, then this is symmetric about the reflection. That is the simplest way to understand this. And if it is symmetric about the reflection, then we will have a sigma plus term. Now we are moving further. If we are having this type of situation, plus and minus. So say this is minus, this is plus. This is arbitrarily designated like this. Or we can say colors are in this scheme. Internuclear axis again. And this is designated as sigma star orbital, which is formed by the combination of pp atomic orbitals. Now, if we are seeing this image, this sigma star orbital in the plane, or the plane which is having the internuclear axis bisecting these molecular orbitals, then we get the same kind of reflection. So if this is green, here is again green. If this is white, if I cut down this, then I will again get this white. So these are symmetric about the reflection. If these are symmetric about the reflection, then we will get sigma plus. So in general, we can say sigma orbitals are symmetric with respect to the reflection in the plane containing internuclear axis. For that sigma orbitals, we are designated the sigma term, molecular term symbol as sigma plus. And this is applicable only for sigma term, right? So we can understand this as we did in case of inversion symmetry. So here I have written the overall symmetry of a configuration is found by assigning +1 to an electron in a symmetric orbital and -1 to an electron in an orbital that changes sign under reflection, and then multiplying the number of all the electrons. We did the same exercise in case of inversion symmetry. Now I will explain it with example. Say I will take the simplest example of hydrogen molecule. We are having this atomic orbital for one hydrogen. This is atomic orbital of another hydrogen. They will combine together to form bonding molecular orbital and antibonding molecular orbital, which are having energies lower and higher than the energies of the atomic orbitals respectively. So here what you can see, we are having two electrons. So how we are going to fill the electrons in the molecular orbitals? So these two electrons, one electron number and electron number 2 will go to the bonding molecular orbitals, designating its molecular term symbol. So before writing this molecular term symbol, we have to write down the electronic configuration. So for this electronic configuration is sigma 1s2. If you are facing any kind of problem, then you can go and check the molecular orbital diagram videos which I have uploaded previous to this series, molecular term symbols. And the reason behind this is that so that we can understand these molecular term symbols in more effective and elaborative manner. So this is the electronic configuration. Now designating the lambda. So lambda for this is 0 because the last electron went to the sigma orbital. So pi, this lambda is 0 because both the electrons are in sigma molecular orbital, for which we are having the orbital angular momentum value 0. And if this is the 0, then term will be sigma. What about this 1? 1 is the multiplicity, that is 2s plus 1. How it comes into existence? So here I am going to solve for you. For electron number 1 it is plus half, and for electron number 2 it is minus half, and if we sum these two, then we will get 0. Right? So we are having S1 plus S2 to S1 minus S2 including 0, or with difference of unity. This whole thing we have discussed in the atomic term symbols. So here what we are having only 0 value, right? If this is 0, then we can calculate the multiplicity. Multiplicity is 2s plus 1, or you can say 2 sigma plus 1. So s is 0, so 1 is the multiplicity. So here this is the term, right? Now we have to assign the parity, and or we can say inversion symmetry. So inversion symmetry is G. How you can say this is G? This is G because sigma orbitals are having plus 1, or they are symmetric about the inversion. So plus 1 for one electron and plus 1 for another electron. So we will get on multiplication these two, we will get plus 1. And if this is plus 1, it means it is symmetric about the inversion symmetry. And if this is plus, then we are designating it as G-red. So the inversion symmetry for these two electron system is G. Now designating the reflection symmetry. So for reflection symmetry, I have told you about this. Plus 1 to an electron in a symmetric orbital. So these two are, since I told you earlier why this sigma orbital is symmetric about the internuclear axis, or reflection about the internuclear axis. So that I have discussed earlier by taking the example of sigma orbitals and pi orbitals. So this sigma orbital is symmetric about reflection. So for each electron we are putting plus 1 multiplied by plus 1, we will get plus 1, and this plus 1 is designated here. So this is how you can write down plus minus signs and inversion symmetry, which is little bit difficult to assign, right? Because we do not know the actual significance of these terms. So this is how the term symbol for hydrogen molecule. You can solve such kind of examples. If your sigma orbital is completely filled, then this will be the term symbol. So without spending any second, you can directly write down like this, right? So for all sigma 2 electron orbitals, you can write down this. Now coming to the next, we are taking the example of helium 2 plus molecular orbital. Now solve this. First write down the electronic configuration. The last electron will go to the sigma star orbital. For sigma orbital, we are having lambda is equal to 0. So for all the electrons, we are having lambda is equal to 0. So the term will be like this. And here you can write down the spin multiplicity. For this plus half, for this minus half, they will be cancelled out with each other. So only plus half will be the value of S. S is the spin orbital angular momentum along the internuclear axis. If we calculate by taking this half, the spin multiplicity, then we are having 2 into 1 by 2 plus 1. This gives me 2. So here is the spin multiplicity. Now writing the inversion symmetry. So for sigma orbitals, we are having the plus G-red. These are G-red and these are un-G-red. So the inversion symmetry will be un-G-red for this electron. What about the reflection symmetry? So we are having 3 electrons. So for 3 electrons, we are having plus 1, plus 1, plus 1. Why plus 1? Because in sigma orbital, all the electrons have plus 1 symmetry about the reflection. You can ask why you have written. So this is for this electron plus 1 multiplied by plus 1, and this having minus 1. So multiply by minus 1. So you will get ultimately minus 1. So minus 1 is un-G-red. That is why this is written as un-G-red, right? This is the term symbol for this H2 plus molecule. If suppose I ask you to write down the electronic configuration for helium 2 molecule. So for helium 2 molecule, we are having one more electron. Now sigma will be the term because all the electrons are in sigma orbital. This is sigma and sigma star. So sigma will be the term. All are paired. So one will be the spin multiplicity. What about the inversion symmetry? So inversion symmetry for this plus 1 multiplied by plus 1 minus 1 multiplied by minus 1 So what you will get? You will get +1. So this will be the G red, right? And what about the reflection symmetry? So reflection symmetry for all the electrons we will have +1, right? For sigma and sigma orbitals, all are +1. So this is how you can write down your term symbol for helium 2 molecule. And similarly, you can write down the term symbols for other molecules as well. Now we are taking the another example of nitrogen. So I hope you now understand what I am going to do. So here we are having the last electrons in the sigma orbital. So for sigma orbital we are having all are filled. So sigma will be the term, all are paired, one will be the spin multiplicity. Since all are these electrons are in pi orbital. So pi orbital is ungeared, right? But we are having 4 electron in ungeared and therefore they will cancel out each other. We will get plus term here. And for sigma orbitals, we are having +1 symmetry. So this will be G again. And now, what about the inversion symmetry? Since sigma is symmetric about the inversion symmetry, so this will be the +1. So as I told you earlier, for the completely filled shell, you can immediately write down this. This is the trick, right? Now I am going to solve for you. So this is how you can write down reflection symmetry for the last 2 electrons, or you can consider all 6, and this will be the term symbol for nitrogen. Now I am taking another example of carbon 2, E2, right? So for that, we are having the last electrons in the pi orbitals, right? So pi orbitals, what will be the term symbol for the electrons if we are having the last electron in the pi orbital? So this is the electronic configuration. Now add the terms. So we are having 4 electrons and 2 electrons are in +1, 2 electrons are in -1, right? This is having lambda is equal to +1. So 2 electrons having lambda +1 and 2 electrons having lambda -1. So in this manner, we are having lambda is equal to 0 ultimately, and this forms the sigma term symbol. Now what about your multiplicity? Multiplicity will be 1. 2 are up spins, 2 are down spins. So ultimately the S value will be 0, and you can write down +½ -½ +½ and -½ You will get 0 value for the S or sigma, right? And if we calculate 2S plus 1, then we will get 1 only. So this will be the spin multiplicity. Now what about your inversion symmetry? Here what should I write? So as I told you earlier, for closed shell you can write down G's directly. Pi orbitals are ungeared, but in pi orbitals we are having 4 electrons. So 1 electron with -1 multiplied by -1 multiplied by -1 multiplied by -1. So ultimately I will get +1. And if I get +1, then in case of inversion symmetry, I have to write down G, right? Now what about the, this is inversion symmetry, inversion. Now about the reflection symmetry. So for reflection symmetry, about this pi, this is very tricky actually. You can think of that we have to write down the reflection symmetry like this, but not. This is not the correct way, right? For this, we have to use +1, +1, -1, and -1, right? So that I am going to explain now on. So this is not actually we are getting the same as I told you earlier. For the tips and tricks, you can write down in this manner, but this is not the correct way to calculate the reflection symmetry. So why it is not the correct way to calculate the reflection symmetry for the pi orbitals? We did this kind of exercise for the sigma orbitals, but we cannot do this for the pi orbital. So this is the question, and this is very important to assign. So we are going to discuss here. One more thing which I bring to your notice, and especially for the physics students, that we suppose this will be the ground state term symbol for carbon, but in physics text, this is written as a ground state term symbol because of the Swan band, right? So that we are not going to discuss here. That is out of the scope of this lecture series. and I will discuss in detail about the reflection symmetry in the pi orbitals in detail. So that is very, very important. Here this plus is correct, right? But this is incorrect way to calculate the reflection symmetry if our electrons are in pi orbitals. So why it is so, that we are going to discuss here.